Yeah, let's start. Before that, okay, let's start. So basically, in social statistic 1, we cover regression. To be exact, or less linear regression. So what is the purpose of regression? What is regression, by the way? That's the question. So, okay.
Do you want us to answer that question?
Yeah. Sorry. Yeah.
Didn't we talk about like a few different purposes of regression?
Yeah, but yeah.
Like, because one is to describe a relationship between two variables.
Mm-hmm. Yeah, and then that's description is one.
Yeah. One is to predict the value of
Right.
the variable.
Yeah.
Outcome variable based on x's.
And statistical inference is the last one.
Right. Statistical inference is the last one. Yeah. But these purposes are basically about theoretical perspectives, like to approach regression. So for statistical sense, in the statistical sense, regression is about regressing the variance of y or changes of y on couple of or a series of predictors. Right? It's about regressing y variable based on or regressing the variance of y based on predictors. Okay. So we're just there are so many variations of y, right? And then we are just summarizing these variances of y in terms of x's variances. So y could be 50 or 40 and 30 and everything. Then we're trying to summarize the pattern of changes in y variable based on x variables, values, and the relationship between y and x variables. Does that make sense? Good. So in the statistical sense, there could be two purposes. The first one is where y would fall. It's about predicting the y value. And how much variation of y is explained. That is another question of regression. Okay. So this is mathematically noted as expected value of y, but not just raw expected value of y, right? We are predicting where the average y would fall given certain x values. Depending on x values, the y variable, the average or expected y variable can be varied. Right? Does it make sense? Or am I making any sense? Good. And then how much of variance of y explained is this is actually how much variance of y is unexplained by x. But anyways, the gist of it is that given that we have the information of x, given that we have information of x, how much variance of y we have? That's another question. Does it make sense? So we're trying to achieve two purposes. Yeah.
Go ahead, you can finish yours.
So we're trying to achieve two purposes. The first one is where y would fall given the information of x's. By regression, we're trying to achieve that. We're trying to predict where y would fall given x variables. And the second one is after you predict the y variable, there would be some variations left, even after running the regression, right? You cannot perfectly predict everything, right? I mean, if you have like millions and millions of variables, then you would have perfectly predicted y values, but this is not the case in most cases, right? So, so we are also interested in how much variance of y explained by the model.
This may be a Soch 360 question, but I feel like I should ask it. Can you explain, when you talk about variance, are you talking about that word is used a lot in this course, and I'm wondering if it's always defined the same way when Felix uses it, because everything is all about variances or covariances, and I want to make sure I'm understanding that well.
Yeah, variance is the measure of dispersion, right? Of a variable. And then this is pretty much the same meaning across all.
Okay. So when Felix talks about the variance of y, is that's the total variance of y, not given values of x? That would be a conditional variance? Or?
So he would differentiate that. But when he says variance of y, it is not conditioned at all.
Okay. Yeah. So that's the whole range of y values.
Yeah.
Okay. Then there's also a specific way to calculate variance of y, right? And that was from 360 as well?
Yeah.
Probably? Yeah.
Sorry?
That was also from Soch 360?
Yeah.
Okay.
So variance of y is it's expected value of y squared, expected value of y.
Okay.
So it's basically about I should explain it very in a step-by-step way. That would be better. So variance is, let's say we have two observations. This is two observations, just one, -1 and positive. And then the variance of, let's say this variable is w, variance of w is for the sample. When you have the sample, this becomes n-1.
Okay.
And then w bar is the sample mean, right? Okay. That means that that becomes 2. So variance is defined the distance from the mean squared distance. This is the distance from the sample mean, right?
Mm-hmm.
And then you square it, and then you sum all of the squared distances, and then divide it by sample size.
Okay.
-1.
Okay. I think I was confused because in his slides he has a different formula for variance.
Okay.
And then on the internet there are other formulas for variance.
Okay.
And so I got into a weird rabbit hole of thinking I didn't know what variance was.
Oh.
Like all day yesterday.
Oh.
So I think I understand.
Let me know if you like came across Felix's definition or something.
Okay,
like that.
I'll find it.
Yeah.
In a second.
Yeah. Sorry. Finish first. Sorry.
So that's a sample variance, and then you
Yeah.
do -1. If it's a population variance, it's just over n.
Just n. Yeah.
So when you say variance is the measure of dispersion of a variable, does that mean the distance between -1 and 1? Is that what you mean?
The
by
distance
measure of dispersion?
from the sample mean. Distance from the sample mean, which is 0, right? Yeah. So did you get it?
But that's what you mean by dispersion?
Yeah. Dispersion is basically dispersion from the sample mean.
And then standard deviation
Is square root of
is square root.
And then, so to rewrite it, this is technically expected value of or this is also mean, so. So y minus sample, which is the distance from the sample. So y variables value is 1 minus 0, which is sample. So that's the distance of y from the sample. And then you square it, and that's the expectation of, and then, yeah. This is the same thing as EY squared minus expected value of y squared minus the sample mean squared. They're the same thing. I don't want to go over how this is the case and everything because time limits, but you can certainly know that. So in Felix's lecture notes, it is most typically assumed that EY is 0. EY is assumed to be 0, meaning that it's centered. If a variable is centered, then 2, 2, 4, 4 is now 1. Because centering is just subtracting the mean, right? Subtracting 3 would be 2 minus 3 is -1. 4 minus 3 is 1. Good.
the homework, there are a bunch of places where we're asked to calculate the variance of things without having all the values of them.
I'll explain that.
Okay.
Yeah, sure. Yeah, sorry. Yeah.
No, that's just, I wanted to make sure you're there.
Yeah, because that's where I was, and I was like.
Yep.
So the first, so the regression line it looks like that. This is population regression. I'll explain why I called population regression model. Called it population regression model. Okay, good. And predicted value of yi is noted as this. So this is the predicted value of y. This part is the predicted value of y, which consists of the intercept and the slope and the x value. Okay. And this is the error term. This is stochastic part. Because it's not a fixed number. Okay. Good. So yi hat is the predicted value of y given certain value of x. That's why there's hat. There's a hat. Hat is used when a certain variable is estimated. In this case, it's estimated by a linear regression model. The estimation sources can be varying, but in this case, it's regression. And expected value of yi, in this case, it can be rewritten as you guys know what's y is this one, right? No? Good? No?
Is there purposefully not a subscript on at the expectation of x?
No. Good. So you guys know that, right? The expected value of two random variables, sum of the two random variables is expected value of x. Oops, sorry about that. And b0 is a number, so expected value of b0 is beta 0 as well. And then the expected value of xi is because it's a number. Right? 2, 3, 4, 69. Right? So that's why it's beta 1 can be taken out basically. And then I'll cover that, but this is assumed to be 0. This has to be 0 actually. So expected value of yi is beta 0 plus beta 1 multiplied by expected value of xi, which implies that when x is at the mean value, then the predicted value of y would be y bar. Good. And then this is just raw variance expectation of y. Now it's condition. This is expected value of y conditioned on xi's. So being conditioned means that xi is now a value. Is now a value. Right? So this is now beta 0, beta 1. X1 plus
X1, not XI.
oh xi. Yeah. We don't have control variables yet, so that's why. Good. So this is assumed to be 0. I'll explain that later. So as you can see, this is the predicted value of y, right? So it implies that given a certain value of xi, the expected value of yi is the predicted value of the regression. So this is expected value of yi given xi is 2. Good. There are many observations like that, but when x is 2, then you expect that y should be about here. About here. Good. That's the purpose. That's the first related to the first purpose of where y would fall. And this related to the second purpose, variance of yi is now can be written as this is variance of but now before going transitioning from here to here, beta 0 is a number, right? So it does not have anything to do with variance whatsoever, right? So it's always a number. So there is no dispersion or variances whatsoever. Does not matter. And then variance. This is beta 1 squared variance of xi plus variance of ei plus 2 covariance of xi and ei. Good. And variance of yi, but I should note that this is assumed to be 0 in OLS. And then the conditional variance of yi again, beta 0 does not have anything to do with variance whatsoever. And then xi is a number right at this point. So they also does not have anything to do with variance. Because we're conditioning on xi. Conditioning on xi means that we are fixing xi on a certain value. We are assuming that xi is a certain value. So it's a number. So okay. But this will be assumed to be equal in OLS. So in OLS, variance of EI does not matter with the level of XI. Yeah. So that's why variance of EI is variance of yi given xi. So what does that mean? I'll explain that in more detail with the graph later, but the total variance of y, or raw variance of y, this is before the variance of y before you run the regression. You have nothing to do with regression at this point, right? Before that, you have total variance of y, and then it can be decomposed into this part. But after you run the regression and then fix, certain values of x's. In this case, it's only one x, but yeah. After you fix a number of x, then variance becomes only variance of ei. Right? So this part and this part is now gone. This is assumed to be 0, practically. So this part is practically gone, right? Does it make sense? So after you run the regression, total variance of y becomes shrinking because you explained the variance of y with your predictors. Does that make sense? After you run, you explain some variances of y, the variances of y, the conditional variances of y, smaller. Good. So this is unconditional variance of y. This is conditional variance of y. And then after you conditioning on certain values of xi's, the variance of y becomes smaller by this component, beta 1 squared multiplied by variance of xi. On a side note, if you don't really understand it, it's fine. But if beta 1 is strong or beta 1 is high, that means that the relationship between y and x is strong, right? So that means that you are explaining a lot of variances of y with x. And then variances of x is also does also play a role here. So if there are much variances of x, then you are more likely to be explaining variances of y as well. So everybody is there's a female variable is an x variable, the x variable right here, but everybody is a woman. Then you cannot explain anything with anything out of y's variances with that variable. Everybody is a woman, so you cannot compare men and women. In this case, the variance is 0, so you cannot really explain. If you don't really understand it, that's fine. That's fine, but that's an implication. Okay, and let's move on to sample regression model. Okay. Now there are hats on beta 0 and beta 1, right? Good. That's because we are using a sample to make an inference about the population regression model. We are estimating the population regression coefficients with the sample estimates. Good. Good. Oh, there should be E hat as well. EI hat. So hats are used when you're estimating something, but the source of estimation for this hat and these hats are different. Does it make sense? So yi hat is the predicted value of y. We're predicting yi based on the linear predictor. We are estimating where y would fall based on the linear predictor. But in this case, you are inferring population based on a sample. There's a difference, right? So in the population regression model, it would look like that, right? That's because you are using a linear predictor. And Before doing that, we should note that b0 hat or b1 hat could mean estimator or estimate. Estimator is a formula to calculate estimate. So beta hat 1 is 3. It's a formula that get the that'll get you the this number. This is a variable, right? Because the components are variables, right? Component variables, you know, they can vary. They can vary. So it can vary depending on the context. When you plug in all the numbers in terms of variances, in the place of variables, then it becomes a number as well. Then it is called estimate. Good. And then when you are this is an umbrella term, statistic. So if it's an estimator or estimate, but the context is that you are estimating some, say, regression coefficients based on a sample, then it is called statistic.
The estimate is called a statistic when you're talking about a sample.
So yeah, either estimator or estimate can be called a statistic when the source of estimation is a sample. Good. Yeah, we have. Oh. Okay.
This is great.
Yeah.
Super helpful.
Thank you. Although, yeah. Anyways, I'm not sure we can go through all of this stuff, but yeah, let's hope so. Ordinary square. Well, less regression estimation is an estimation technique. And then this is the short abbreviation for ordinary least square. So it's a technique that when you have these observations like that, it's a technique that finds this line. Okay, good. Good. And how does it find the regression line is or so the predicted value of y given x is say 10 is right here, right? But the actual value can be right here. This is y hat. So this is error. So ordinary least square is is a technique that finds this line that makes the sum of squared errors minimized. Sum of squared errors should be minimized. Good. Questions? And of course, to do that, the sum of all errors should be 0. Because, it would make the sum of squared errors like really, really large or something, right? So that's why the sum of all errors should be 0.
Is it the sum of all errors or the sum of all errors squared?
The sum of squared errors should be minimized, and then sum of errors should be 0.
Is the sum of squared errors the same thing as the variance of the error?
Except that you have to divide it by sample size, but
So the variance of the error is the sum of squared errors divided by the sample.
except that it's technically n minus k.
Okay.
For some reason. I don't want to go over like why this is n minus k and everything, but basically sample size. Good, good. According to OLS, in Search 361, it was a known fact that you didn't drive anything, but we just learned that. We just memorized that basically. Or so this is covariance, right? You guys know that. And this is the variance formula. And then beta 0, which is not so important. But this is coming from the fact that E of yi is beta 0 plus beta 1 E of xi. When it's stable, it's y bar, then it's x bar, right? And then you solve for beta 0, oops, then you would have this one. Good. If you don't understand it, you don't have to look at it. So what was the implication of beta 1 hat being covariance of xy divided by variance of x? beta 1 hat is basically covariance of xy, how much they covary. Right? And then divided by some variance of x. Okay. And we covered assumptions, OLS. The first one is linearity of the relationship. I think it's pretty straightforward. So for example, when the two variables have a curvilinear relationship, this assumption should be violated, right? Because when you run the regression, it'll show you 0 as a coefficient. Right? And the second assumption is no perfect collinearity. Meaning that one variable should not perfectly explain the other. I'll explain that why in more detail, but that's the second assumption. And then the third one is almost get nasty. So same variance of errors cause x. Yeah, so basically it's about errors are not, when you run the regression, somehow here errors are practically 0, but somehow it gets larger and larger. And the fourth one is unrelated errors. So errors should not be related to each other. So for example, so when you're plus sample families and then you are serving all of the members as your respondents, they would have similar errors in terms of happiness level or something like that, right?
Can you explain that again?
So when you're sampling families first, and then you are asking survey questions for all of the family members, and then they would have error terms like 10, 10, 10, 10. Pretty much similar, right? Because of the shared characteristics that we cannot observe, really.
So you're assuming there's no.
Huh?
You're assuming no.
Right. So in this case, this assumption should be violated. But we assume that this is not what's happening at this point.
Assuming.
Yeah.
Thank you.
Okay.
So this is the same as the first I.
Yeah. I'll note that. And errors are normally distributed. There are more assumptions of OLS, but on the 361 level, that's what we have covered. So note that this is not y or x. So the y variable should not be necessarily have to be like a normal or x variable. In practice, when y variable is really skewed or whatever, then sometimes it's error terms becomes non-normal, but it's not supposed to be happening by CLT. I'll explain that in my office hours if you are interested about it, but let's just stop right there. So to summarize these three assumptions, it's noted as EI is IID, independent and identically distributed as normal distribution.
Which one is that?
Sorry. Summarization of these three assumptions. Yeah. It's this. EI follows normal, independently and identically distributed as normal distribution.
Independent and identical distribution.
Independent and identically distributed as normal distribution. Good. And you can see that the the mean is 0, which is obvious, right? But you see that sigma right here. The next question would be, where does this sigma come from? Right. So to do that,
I have a silly question. What is the squiggly single equal sign?
this one?
Yeah.
This means follows. EI variable follows normal distribution. To explain where does this sigma come from, I'll I'm sure the students who took my last semester would remember it, but this is y bar. And we are using sample. So this is sample standard deviation of y, which is not conditioned at all. So this is sample mean, right, of y variable. And then the measure of dispersion of this variable is now standard deviation of y. And then there's a hat right here because it's a sample. It's from a sample. Does that make sense? No? Good?
I don't understand why you drew it that way.
Huh?
Can you explain why you drew it that way again?
Oh, y variable?
Yeah.
So y variable can be, this is the y-axis, right? So this can be 10 and 20, 30, and everything. So there are relatively small number of people with 10s as y values. And then there are many 30s, many 40s, 50s. Does that make sense? Or good. And then the measure of dispersion can be summarized as the standard deviation. Simple. Yeah.
So the total dispersion isn't one standard deviation, right?
Sorry.
I'm trying to figure out if I'm asking this question correctly. When you say dispersion, standard deviation is like you're going. That's a normal curve that you have drawn right there, correct? So the dispersion
it doesn't have to be normal, but
or like I think what I'm trying to ask is that's standard deviation, not variance.
Yeah, standard deviation.
Okay.
Yeah.
So
But if you square it, it would be variance, right?
right, but every value in that curve that you've drawn isn't between one standard deviation and -1 standard deviation, right?
No, it's basically like how the actual data distributions. There are like it can be in like that.
Right.
There are so many people right here, then it would be a lot.
Yeah. I guess I'm just confused as to why you're saying the measure of dispersion is one standard deviation.
Oh no, just standard deviation is just a measure of dispersion.
Just standard deviation in general?
Yeah, in general.
Okay,
That's-
not one standard deviation.
Yeah, just
That's where I was confused.
Oh yeah. Good questions. This is unconditional standard deviation of y. This is before you run the regression. This is the how much the data are dispersed before you run the regression, right?
Does unconditional just means running before, and
Yeah.
you're saying that because you haven't yet conditioned on something in the regression? That's what that means?
And then we would have this regression line, right? And then there would be errors, right? And then you square it, and then add all of the squared errors. Add all of the squared errors and divide by n minus 2. Just I get this is yeah, I don't yeah, it's too much. Just this is n minus 2. Let's just memorize that.
Will always be n minus 2?
No, when this is actually n minus k, in the sense that k is the number of predictors.
Is that degrees of freedom? Is that
Yeah,
the same?
yeah. So technically, like when you're the expected value of certain certain variable x is just sum of all values divided by degrees of freedom, actually. Degrees of freedom is how much information, free information you have. Yeah.
Is it just because we, sorry. Is it just because we estimated two pieces of information? The two, and then
Yeah, so we are just, estimating beta 0 and beta 1, right? We are estimating two things. So that's why we have 2 degrees of freedom taken. So we do know now that beta 0 and beta 1, right? So we fixed these 2 information. That's why it's n minus 2. Yeah. Yes.
That formula, is that for the variance again?
So this is variance of EI. Yes.
Django.
In
The homework we're asked to estimate the variance of E without any information about the values of Y or X. nothing that we've covered would tell us how to do that.
There's a y, there's a beta. This is actually there's a y. You can use that for. Oh, what was the question?
My question is just in the homework for like question 5. We have no information about the variance of y. We're supposed to estimate the variance of the error term.
Yeah, I'll explain. You
Okay.
you should know the definition of r squared.
Okay.
You should understand the meaning of r squared. I meant to go over that when I cover r squared, but yeah, okay. There's a lot to cover, but yeah. Okay. If you're interested in the concept of degrees of freedom, you can just start again. But yeah. And then if you square, this is noted as sigma hat squared. This is conditional variance of y. Good. After you condition on x variables, there are some variances. And then this is obtained by getting the, summing all of the squared errors and divided by sample size. Because even if there is a crazy observation like that, you would assume that variances are the same across all x's, so you are just averaging them out. And then assume that conditional variance of y, same opposite observations. Good. Good. Okay. All right. This is called. Yeah, I'll cover it. And we should also cover hypothesis, the statistical inference based on OLS estimation. You guys understand the basics of statistical inference, right? You guys know sampling distribution. No? Okay. Yeah. So what is the two approaches of sampling inference?
Hypothesis test and confidence intervals.
Yes. Confidence intervals and hypothesis test. CI is basically beta hat plus minus alpha 2. Hypothesis testing is basically, which is typically 0. Typically, beta is assumed to be 0 in null hypothesis, typically, right? And then this is t statistic. So the customary threshold is that when the t statistic is more than 2, then you reject the null hypothesis, and when it's less than the absolute value of 2, then you fail to reject the null hypothesis. Right?
Can you explain or read out the formula for?
Oh, what percent? Oh.
Yes, that's just.
Oh, okay. Sorry.
Can you explain or read out the confidence interval formula?
Beta hat plus minus t of t statistic at alpha divided by 2 and standard error of beta hat.
What is alpha?
Alpha is the confidence level.
What's the level?
Yeah.
Interval or level?
Confidence
The
level.
Okay, thank you.
That's not times the standard error.
The time standard.
There is a little, okay, I didn't see that. Okay.
Yeah. Good.
And the standard error of beta hat is the square root of the variance.
Divided by or
And that the variance, the sigma up there is which sigma? The sigma of
sigma conditional variance, conditional standard deviation of y, which is this one.
Okay.
This amount.
I'm sorry if you just got this, but in the hypothesis testing star, what does that mean?
B star is the beta, the population beta that is assumed to be in the null hypothesis. Oops, sorry. Great. So it looks like it's basically the same thing as sigma hat, only divided by some numbers, but they do have different meanings. Okay? The sigma hat is about how much dispersed y is after you run the regression, right? But this standard error is standard deviation of sampling distribution. I'm sure you guys know sampling distribution, so I'll just move on. Yeah.
Wait, sorry, I think I might have missed something. So you said the sigma in the numerator is the dispersion of y after you run the regression, so it's the
conditional standard deviation of y. Good.
Which is equal to the variance of the error.
Equal to the square root variance of the error. Yeah. So basically variance of yi hat yi given xi is basically the same thing as, they're the same thing, right? Does it make sense? You run the regression and there's still variance of y. That means that is the same thing as variance of error terms. Good. So, yeah. Questions? No? Okay. Should we take a break or keep going? Sure. Okay, we can take 5 minutes. Yeah.
Sorry. That's the standard. What's the variance of beta hat? Or that's the standard error of beta hat?
This one? Yeah.
That's the standard error of beta hat. The
Right.
variance of beta hat is that square.
No, this is the standard error, standard deviation of the sample distribution, right?
Yeah.
And then this would be the variance of sample distribution. And then this is conditional variance of y. And then, sorry, this is conditional standard deviation of y.
Okay.
And this is conditional variance of y.
But so in Felix's like problem set notation, this is what he calls like variance of beta hat.
Yeah, that's correct.
And this is when he asks about the standard error of beta hat.
It's a lot though.
I feel like it should just be a separate symbol.
Yeah, I know. That pisses me off. That's just like, these should be two different symbols. There are so many letters in the Greek
I was
alphabet.
gonna say for just so gung ho about using Greek letters for everything.
It's the same Greek letter. How you doing, Isaac?
Good. It's been great. Oh, you want to yeah. She sent me this. Oh, so.
Do you graduate after this semester? Bet you're so dumb.
Very much so. It's just been like a year like waiting, I feel like.
Yeah.
So one more year.
One more year. It's going by too fast. I have to apply for things. I'm just like, to get everything scheduled.
What are you applying for?
I'm applying for MPH programs. But I have to figure out which ones that I want to apply to and make sure I take the GRE. So it's coming up faster than I expected.
Yeah, I noticed you did it.
Are you still moving to New York? Is that it? When?
July 13th.
Oh, it's close.
I know.
Are you excited and nervous?
I'm really excited. I just like don't know how I'm gonna get everything out there.
Oh, yeah.
Oh, you're not like shipping anything. Just taking suitcases. It's really, yeah.
It's expensive to ship things.
And so, well, especially like I would have to ship in California, and that's just like I don't want to do that.
No.
And like I want to be able to buy everything there anyway. So it's like there's no reason
What is
to.
happening?
Yeah, then you have all the double stuff.
Yeah.
Something I'm considering too. I'm like, I don't know how to get all my stuff to any of the coasts. That would be interesting.
Yeah, I would like want to like leave or like sell things here. Like I'm not taking it home.
Oh, yeah.
Yeah. It's gonna be fun. Awesome. Sorry, I'm just like manhandle your notes.
I can't sit in these chairs for that long anymore. Too old. So hard.
internship for the car program, and I've been working with a researcher. I think he would like me to stay for this.
Wait,
And
what
we're,
is doing?
as a
So
population
why
health
is
institute, he does
the
work on
expectation
recovery
of the error
And-
terms that varies? Because
That's
so it's subtracted from the
But then
mean
somebody
versus
from
the
my
mean.
hometown commented,
The expectation of the
contacted
error
me,
terms.
does they do public health policies?
Not the expectation.
The expectation of the
Trying to
squared
like
error.
weigh
Right, so
overdoing
why
it.
isn't it subtracted?
We're getting
Because
all
we
this-
assume that the mean of the error terms is 0 based on OLS assumptions. Right.
Okay.
Based on OLS assumptions, the mean of the error terms has to be 0.
Yeah.
Well, it sounds like you
That tracks.
My strategy is just anytime there's something I don't understand, I say it's based on OLS assumptions. Christina, this is how you're spending your birthday?
I know.
Oh, dedicated students,
Hardcore.
Just type in lesson on 3.
Yeah.
Finish that conversation.
Yeah.
I agree, or it's just great.
I would work to associate.
Oh, yeah.
Like usually come from urban centers because
Lesson.
the geography makes it so you can shut down.
Yeah.
That's what she was saying.
There's a logic to the argument you're beyond that, which is just that like
Outlet,
the state is urban
Oh.
central.
Yeah, and it's the best.
Closer to
It's my
figures in the
favorite
state.
restaurant.
Being
Like that face.
I don't know.
yeah, and like you're just like
We tried like the other type of.
like built that
Yeah.
perfectly.
Uh,
I didn't really like her. I need to figure out a way to like do
It's better than
that.
mine.
This is so much better.
Like she like doesn't
Yeah,
really
it's good.
like interested in what
So
she teaches,
good.
but she's like so explicitly not US focused.
It will, it might be.
Oh no.
Yeah,
In the sense, well, like, but even in a more direct sense.
They just like.
I'm taking it right now.
Yeah.
Food poisoning.
Yeah.
Keep thinking about it.
Oh, yikes. Wait, did you not get it or did you
That's
not?
I would, but I got.
Oh, yep, so probably.
Good enough.
One of my characters is vegan. She's allergic to. She's like basically lag and she's like lactose intolerant. Like she's literally doing it all.
Yeah, I saw it.
So I'm super
Season
lactose
2.
Someone- Yeah.
They're like all out together. Who do you think they're gonna kill? That would be the surprise, right? Like we expected to be such a killed out, or yeah, like choices.
Haley?
Like
Nikki Haley? Yeah, she's kind of like, what do you call it? Black sheep or dark
Yeah.
horse? Dark horse, that's what I'm thinking.
She's the one who like
I mean,
becomes nice, right?
Um,
think the killers.
yeah.
In the overall. With the question.
Yeah, let's start. Yeah. So next, we're covering multivariate regression, which means that we are adding control variables. So it looks like that. Basically, regression line looks like that when you're using samples. Expected value of yi, I think it's pretty straightforward. Oh, sorry. Nope, that's correct. And conditional. I think these are pretty straightforward. Variance of yi is a little tricky. So if we plug in this part in the place of yi, the right side of the equation into yi, and then just distribute all of the terms, then you would have this part, this side of the equation, and then this part should be 0 in OLS. And the remaining part is beta hat multiplied by variance of x1 plus beta 2 hat multiplied by variance of x2 plus variance of error terms plus 2 beta 1 hat make beta 2 hat covariance of x1 and x2.
Should beta 1 and beta 2 be squared?
Oh, shoot, sorry. Yep, that's correct. Good. So that means that variance of y is now, after running the regression, it can be decomposed into the relationship between y and x1 multiplied by variance of x, and the relationship between y and x2 multiplied by variance of x2, and the error term, as well as covariance of x1 and x2. This part wasn't there in bivariate regression model, right? So running regression means that you are decomposing into decomposing variance of y into error terms, as well as explained parts, which consists of each variable's variances as well as covariance of x variables. Okay, good. Sure, my laptop is okay. And then the logic is same. In OLS regression, the error terms squared, the sum of squared error terms should be minimized, and then the sum of error terms should be 0. Right? That's straightforward. I want to mention how controlling works. The first step is run a regression of x1 on x2, and then there will be error 1 variable, which is a variable. Error 1 is a variable. Right? When you have like that, you basically have error terms, right? For each observation, you are making a variable out of it. For example, this is -1, this is 2, for example. Then the EI would be -1, -1, 2. So this is let's say it's E1I. Okay. This is a variable. And the second one is second step of regress Y on E1. Okay. This is basically linearly subtracting linear correlation between x1 and x2.
So in this model, do we have y, x1, x2, and e? Are those the 4 variables that
No. So after you run the regression of x1 on x2, there would be a new variable called e1 based on the error terms you have.
Okay.
And then you run the regression of y on e. So there are 3 variables in your data sets.
Gotcha.
But yeah, Stata makes the error terms. Gotcha. Yeah. Good. I mean, Stata does not literally do that because it uses matrices and stuff. So, but the principle is this one. Yeah.
So when you write linearly subtracting linear x1, x2, at what stage are we? At what stage are we doing that? All of this, or disconnect that?
So this is in the first stage you are doing linearly subtracting linear correlation between x1 and x2. Right?
You're subtracting it, or you're just finding it?
So basically, x1 hat, where x1 is defined by gamma 0 plus gamma 1, x2 plus E1, right? When you're running the regression, x1 variable is now in the linear regression, in the linear relationship between x with x2, right?
Yeah.
And the error term is E1. Right? And then you are moving these parts into the other side of the equation. That way, you have linearly subtracted all the linear relationship between x1 and x2. So for example, we are talking about a little bit of Swiss 2 at this point, but let's say women lower paying jobs, low paying jobs, and then this is wages. So the story here is there are so many women in lower paying jobs due to undervalue of women's work and everything for female dominated occupations. That leads to wage gaps between genders, right? That means that when you are linearly subtracting the proportion of women in lower paying jobs out of it because of women are there, then there is no relationship whatsoever now. That's the assumption it's making. That's based on some series of assumption, but it's saying that when we linearly subtracting the overrepresentation of women out.
So it's the same.
Right. And then we would have this relationship. And yeah, and then yeah, we would have this relationship. In this case, you are controlling for women. Good? No? Good? Okay. Good. And then I don't want to repeat all of the sigma hat shenanigans, but it's now sum of the I squared divided by n minus k.
Sorry, what are we referring to?
This one?
Yeah.
This is conditional standard deviation of y after you run the regression. So this is unconditional one, unconditional standard deviation of y. But if you, after you run the regression, you would have some remaining variance, right? And then this is measured as sigma hat, the dispersion of error terms is measured as sigma hat. And then this is now calculated by sum of all errors divided by n minus k. K is number of predictors plus 1 for the intercept. So in this case, if you control for x2, then the x's variable should be e1. Good. This is yeah.
Can you just repeat that sentence again? If you control for
x2, then this should be e1. Or sorry, this should be all the x values, all the x variables.
then all the x variables have the same error term, what you're saying?
So yeah, so I mean, so basically after you run the regression of multiple regression, there should be some variances, right? And then that is the conditional variance of y.
That was the conditional standard deviation.
Oh, conditional standard deviation, sorry. Conditional standard deviation of y. Oh, sorry. Conditional variance of y.
Up there too?
I just forget a lot about mean squared terms. It's confusing though.
Wouldn't that have been the standard deviation though without the square?
So without the squared, it would be conditional standard deviation of y. And if that's the case, it should be this one. Right. Good. Don't think about this x-axis at this point. It's it's a little confusing. You should use matrix to. Oh. And then standard deviation of beta 1 hat is now sigma hat divided by and minus I'm pretty sure it's K. Oh, no, sorry. This is 1.
And their gamma sub 1, 2 is.
Yeah, I'll explain that. So this is basically the standard. This is standard error of beta 1 hat, right? This is the same thing when we looked at the standard deviation of X in bivariate regression models, except that it has now relation squared. R12 is a correlation between x1 and x2.
And the symbol you use for that is what?
R.
Oh, that's an R. Like a little baby R?
Yeah. Oh, yeah, this is R, sorry.
Right, I have another silly question. I don't understand why there's the 1, 2 there. The R.
X1 and X2. Correlation between X1 and X2. That's why it's 1, 2.
Okay.
So that means that, yeah. So that means that if the correlation is 1, meaning perfect collinearity. So knowing one variable explains all of the other variable, or knowing a couple of variables perfectly explains the other. Right? That means that correlation between certain variables and the other variable would be 1. If that's the case, 1 minus 1 is 0, right? And the standard deviation would be infinite. Right? No? Questions? So if in the case of perfect collinearity, standard error would be infinite and thus undefined. Questions? Yeah.
What's the difference between the correlation of x1 and x2 and the covariance of x1 and x2?
Covariance
Square root.
Oh no, sorry. That's not true at all. Standard deviation of x1.
Oh, this is the question you answered.
Just for clarification, so the only time you'd have perfect collinearity, it would have to be literally the same variable.
So if they have really high correlation or something like that, they have a really high correlation or something like that, the standard error gets really large.
Right, but this problem of perfect collinearity.
Yeah.
Yeah.
Exactly one, yeah. So that means that standard error is infinite.
Alright.
Yeah. Good. And then we also covered decomposition of sum of squares. Oops, not I. There's no I. Let's see. Oh, my battery is on. Huh. I don't know what to.
You need to check your-
Oh, yeah.
This
Yeah.
one is old school, so.
Oh, you.
I don't know if it's the right size for you. But
I don't think so. Mine's this one, so.
great.
Thanks. And good. Good. So this is the total sum of squares. This is basically this is total sum of squares, which means you how much your observations are dispersed. Right? Except that you didn't divide it by the sample. Right? This is raw sum of all distances squared. Right? Good. No? Good. And then you are decomposing it into explained variance of y, which is called MSS. Oh, by the way, this is TSS. Model sum of squares. Which means that oh, sorry about that. This should be explained variance. Sorry about that. Good. And then this is unexplained variance of y. This is this is called SSE, sum of squared errors. So the implication of this equation is basically total sum of squares, which is the raw variance of y, except that it's not divided by some number, can be decomposed into explained parts and unexplained parts in the additive sense. And and then degrees of freedom that corresponds to this part is n-1. And this part is minus KO. K minus 1. And this is n minus K. Good. So basically, it's about especially explain parts of y. You know, and I'm sure you guys know this part, you're familiar with this part now. But for this part, this is about explaining parts of variance of y. Okay. This is basically y bar. Without any information of x whatsoever, you expect that y to be here. Just for all observations. That's the expectation, right? You expect that y to be here. But with the information of x and the help of linear predictors, you are predicting that, oh, yi should be here when x is, say, 10. Right? So this is y bar, and this is yi hat. But let's say the actual yi is right here. Then this is explained parts. So you have a better sense of where y would fall with the help of linear predictor, right? But still, you have unexplained part of variance of y. Good. That's what it's talking about. Okay. Can I erase that? Okay, sure.
It's not the graph yet.
Oh, okay, yeah.
Can I ask a quick question?
Yeah.
So for the flat line with y bar, is that just if we have no other information, that means the average of y?
Uh-huh.
So that's what we're taking there?
Yeah. So with no information whatsoever, you expect y to be on average, right? So that's
the
why.
best predictor we have in that scenario.
Yeah. So that's why it's called expected value. That's why it's called expectation. Yeah. Does it make sense? Question? And then this the idea of r squared coming from this. R squared is about how much you explained divided by the total variance of y. So of the total variance of y, how much you explained is what r squared is measuring. Okay. Good? No? Okay. So this is the same thing as variance of y hat and variance divided by variance of Ben, can you pull up the question you had like before? Yeah. I have a laptop right here, so.
Problem 5 on the problem set.
Right. Y is 6.6. And then
And r squared is 0.52.
And the first question was, what was it?
What is the variance of the error term?
Variance of the error term. That was the first question. So, by the way, y variable is standardized, right?
Yeah, everything's standardized.
Yeah. Every variable is standardized. So standardization means that, you know, the mean is 0 and the variance is 1, right? To get the variance of E, what we have is right here, right? So to connect E and variance of E, you should take variance in both sides of the equation. Right. And this is 1 because, you know, y is standardized. And this is 0.6, variance of x1, 0.6 squared, 0.2 squared, x2, variance of E, and 2, 0.4 variance of because x1 and xe and x2 and e are independent. They are assumed to be independent, right? So we did not count that. Okay. And this is 1. These are all 1 because they are standardized. Variance of x1 is 1 because it's standardized. And the same thing for x2 as well. Good. Oops. Yeah. I should have not. Oh, sorry about that. I made the same mistake. Yeah, that is one thing you can go, one way you can go to, but So, but we don't know covariance, right?
That's the next thing we have to solve for, so leave that up.
Huh?
That's the next thing we have to solve for, so leave
Yeah.
that up.
Oh,
I'm confused where that came from.
Huh?
Where did the code, I don't understand where that code came from.
so variance of when you have that, variance of something plus 2 multiplied by 1.6, 1.2, covariance of x1 and x2. You know a plus b is variance of a, variance of b, plus 2 covariance of a and b, right? And this method was not correct because we don't know covariance. Then we should use this information, right? Okay. We know this information is variance of y and divided by variance of y hat divided by variance of y. This is 1, right? So variance of y hat is 0.52. So this part is y hat. So variance y is variance of y hat. And variance of y hat, variance of e. We assume they are not related at all. So from that, this is 1 and this is 0.52. So now we can say this is 0.48. Okay, no? Yeah.
Winship just gives the formula for the variance of the linear combination of variables for 2, but I think you've used it for 3, combination of 3 variables a few times. Can you just show us what that is?
3 variables?
Yeah, so like a plus b plus c.
Oh, okay, I see.
Yeah.
Yeah.
And so what you had it before also about the variance of y,
Uh-huh.
so you said that wasn't correct?
Oh, that approach was not proper in this question because it's blocked. And then so I try to find the pathway to get the to get here, right?
Okay.
But that wasn't the pathway was pretty much blocked because we don't know covariance of x1 and x2, right? So instead, I use the different approach, and then use this information right here, which is variance of y hat divided by.
Am I the only one who would want to see that second approach again?
Okay, yeah, I can show you. But before that, let's cover this one first. Okay. This is how the formula works.
So, because if you were added variable d and then variable e, it gets very complicated and long. Is that the reason that we're shifting to using matrix algebra?
Oh, this one?
Yeah, like
Um,
what am I trying to say? I'm wondering why instead of just doing all of the work like this, why are we using matrix algebra?
yeah. This is a part of the reason, yeah.
Okay. Like it
That's
just
true.
gets really complicated when you have more than 2 or 3
Right. Yeah.
covariates.
Because you have like 20 different variables or stuff like that.
Yeah.
You don't have like so all of it.
Right. Okay.
But I'll show you how to solve this question again in a clearer manner. So the question is variance of E, right? And we have E right here. So the way is variance of Y, variance of right? But if you lay out all of the components, like distribute all the components, you would have to have covariance of x1 and x2, which we don't know, right? So you shifted your approach to y hat approach by equating it as y hat because we want to use that piece of information right here, r squared, which is variance of y hat divided by variance of y. Does that make sense?
That very last sentence again, I think I got you.
So did you understand like the shift of approach? And then we know that r squared is variance of y hat divided by variance of y, which is explain the variance of y, right? And divided by total variance of y. Good. Good. So variance of y is 1 because it's standardized, or y variable is standardized. So that makes variance of y hat 0.52. Right? Good. And then now it's variance of y hat plus e, and then variance of y hat, variance of e, by the S assumption. So now this part is also 1 because y variable is standardized, and this variable is 0.52, and that makes variance of e 0.48. Does it make sense? Good, good.
And then we would use the other covariate, the formula with the covariance to find the
Oh. The second question.
The second question is to solve the correlation between x1 and x2.
Oh, okay, yeah. Yeah, so we know variance of, right? or variance of y. So the next task is covariance of x1 and x2. And we have to get the covariance, you should take variance, right? We know this number, right? We know this number as well from question A. Now we can solve the equation for covariance of x1 and x2.
Because they're standardized, the covariance and the correlation are the same thing.
Yeah. Good. We don't have too much time, but
Can you put you just
okay.
read, just like that?
Yeah. And we also covered f-tests. This is basically about how much variance the model explains by the introduction of certain changes in the model, and whether it is substantial enough or significant. Do you want me to write that or this one? Okay, sure. How much variance the model, variance of y, right, explains So for example, it's about how much variance of y the model explains by adding, for example, gender and race in the model at the same time. So note that, so this is about whether, this is not about whether like race itself explains the variance of model enough or explain the variances of y enough, or gender in itself explains the variance of y enough. It's about if you make a change that you introduce the both of the variables in the model, then it's about how much that introduction of these two models, these two variables, explains the variance of y enough. Okay. This is divided into global or walled f-test or partial f-test. I mean, f-test itself is wall test, but yeah.
Just going back to the previous system for a second, this is like a substitute for testing. This is test of each data.
Right. So the yeah, I was going to mention that, but the null hypothesis here is in the global f-test. All of the beta coefficients should be 0. So by comparing no predictors situation and then k predictors situation, you are comparing these two situations. This is full set of predictors you are including in the model. You are comparing these two situations and then compare how much variance y has. After the regression. No predictors means that there is no regression whatsoever, right? You're comparing these two situations in terms of unexplained variance of y. So that's why the null hypothesis here is all of the beta coefficients are 0. So compared to no predictors whatsoever, your null hypothesis that there is no additive variations explained whatsoever because of the introduction of these two variables. And the alternative hypothesis would be beta 1 is not 0 or beta 2 is not 0 or etc. etc. Beta k is not 0.
To catch a bus. I'm sorry, I'm not going to be home until super late. I'll get that from you tomorrow.
Yeah, sure. Yeah, that's yeah.
See everybody. Good luck.
Good. Partial f-test is basically about partial changes in the model. For example, you are comparing K predictors models, you introduce like K predictors in the model, but you are comparing this model with K predictors plus gender, for example, or gender and race.
This is for the partial test.
So you have variables in the model already. That's why it's not global f-test or something. Global f-test is about like including is about all of the variables in the model, right? But in this case, it's a partial f-test, which means that compared to K predictors, adding these two variables, whether adding these two variables substantially explains the variance of Y. That is the question. That's the partial f-tests are all about. Yeah.
So down there, are the global and all that tests the same as the general linear test?
Yeah. It's, yeah. So in this case.
Oh, K predictors plus gender
And
race.
race.
Oh, okay, so just.
So in this case, the null hypothesis is the race, the gender are all 0, and then this is good.
For the alternative hypothesis, it's just at least one of them doesn't equal 0, right?
Right, just 1 or 2. Just one is enough. Yeah. So that means that when beta is not 0, that means that you are substantially explaining or predicting the variance of Y. Right? You somehow have a clearer image of where Y would go. Right? Yeah. The F statistic is SSE of the reduced model and the SSE of the full model, degrees of freedom of reduced model. Okay. Good. This is basically comparing unexplained variance of Y in the reduced model, which means in the global f-test, there is no predictors whatsoever, right? That means just raw variance of Y. And minus unexplained variance of Y of the full model. So you are comparing how much you are comparing unexplained variance of Y. Right.
And what's the R again?
Reduced model.
Reduced.
What is the next line going to say?
Degrees of freedom of reduced model minus degrees of freedom of the full model. Degrees of freedom is defined as n minus k in the model. K being number of predictors plus 1 or intercept.
isn't the reduced model 0?
So this is unexplained variance of y in the reduced model. So this is raw variance of y. Right? What do you mean by 0? Sorry.
Like when we do the F test,
Uh-huh.
we're comparing when there is no beta or beta is 0
Uh-huh.
to the alternative.
Sorry. Oh, no, sorry. No.
Never mind.
So when beta is 0, there should be no difference between the full model and the reduced model whatsoever, right?
Yeah.
But then beta is not 0, then there should be difference, right? In terms of unexplained variance of y.
But then that's gonna give me a number, and then how do I make sense of that number? Yeah.
So this one?
No, like after.
Right, yeah.
Or
So-
after this time.
Yeah, I'll do that. This is basically about comparison between reduced model and full model in terms of unexplained variance of y. Then you would have, for example, 20 or something like that, right? And then the F statistic as the degrees of freedom of comma this one. These would. And then this is the F distribution with these degrees of freedom. And then you have 20 as your statistic, and that's your p-value. When the p-value is less than your threshold, for example, 5%, then you reject the null hypothesis that all of the betas are 0. Good, yeah.
So the F statistic just has 2 degrees of freedom.
Right. Yeah, F distribution has 2 degrees of freedom.
You use the latter in order to calculate. Use the second one to calculate the feedback.
No, so these are 2 different degrees of freedom.
Right.
That you need these 2 to identify this F distribution.
Oh, okay.
Good. And the relationship between t-test and f-test. So when it's the same thing as f-test. Oh. Which means that you have the t distribution with the degrees of freedom of n minus k. And then if you square it, meaning that if you have 2 as your observation, you would have 4 as your observation, and then you do that, repeat that the same thing for all of the possible observation step right here, then you would have this distribution.
What is F something?
Oh, 1 comma n minus k.
So
This
there,
is F distribution, degrees of freedom of n 1 comma n minus k.
so the degrees, so t squared equals f1, the degrees of freedom are the same.
Sorry?
So the t test squared is the f test when the degrees of freedom are the same.
So with t squared, t statistic squared is the same thing as f statistic, only when there's only 1 degrees of freedom right here. Which means that degrees of freedom of the reduced model and the degrees of freedom of the full model has the difference of 1, right? So n minus k of the reduced model and then n minus k of the full model is 1, right? So it's just 1. So you introduce only 1 variable in the model, which means bivariate regression. Does that make sense? No? Good, good. But it diverges when Q is not 1. Good.
What is Q?
Just any degrees of freedom that's not 1. Okay.
It diverges.
Yeah, it diverges. Good. It means that T being significant, meaning that a beta hat is really large enough or something, is not necessarily equal to explaining much variance of y in terms when you are introducing multiple variables. So each variable's significance does not guarantee the much explanation of variance of y, if that makes sense. Because that is related to this one actually. Variance of y is variance of beta 1x1, beta 2x2, right? And if that's the case, blah blah blah, 2 beta 1, beta 2, covariance of x1, comma x2. So if you decompose it, decompose the numbers of variance of y, one of the components is that is about covariance of x1 and x2. not just variance of x1 and x2 and e. Right? So they don't have to be significant, but somehow they can explain a wider variance of y because they have so strong covariance. Right? That's why they diverge. Good. And then even if they are significant, that doesn't necessarily mean that you're explaining much variance of y, because it's about joint distribution. The distribution format is different. The F distribution form is different from F distribution as well, but more importantly, covariance can be affecting the variance. Even if they are significant, it can be affecting the total explanation of y by the introduction of these two variables. If that makes sense. Does it make sense? I don't know. That's why it's divergence. So the t-test and f-test are two different approaches with different meanings, really. They generally agree with each other in the sense that a t-test is about how the relationship is strong between the relationship between x1 and y is strong enough. But the f-test is about how much variance of y the model is explaining. There are slight differences. So when there is only one variable, right, only one variable in the model, they are bound to be same, right? But when they have more than one variables in the model, they can diverge because of the covariance of x variables. Okay. Yeah. Good. And then lastly, no, not lastly, but sorry. We can look at data outputs that was uploaded on the course website, but I can replicate that on the board. So for bivariate regression, we run a regression prestige and an R-inc. This is income variable, and then this is the occupational prestige, right? And the data output shows you model, residual, and total. And it shows you SS, EF, and MS. This is model sum of squared, and then this is SSE, and then this is total sum of squared. This is explained variance of y, and then this is unexplained variance of y, and then this is total sum of squared. And then degrees of freedom is k minus 1, n minus k, and minus 1. If you add these two numbers up, you would have this. It means that the total freedom was n minus 1, but after you estimate k regression coefficients, or k k minus 1 regression coefficients, you would only have n minus k freedom. And then you would have the average of MSS, explain parts of y. And then this is MSC, mean sum of squares, which is the same thing as conditional variance of y. And this is basically variance of y. So, So this number can be obtained by dividing MSS by k minus 1, right? That's how theta output is shown. And then that implies that how much variance of y is explained per regression predictor, right? And then this is about MSC, or conditional variance of y, and then this is variance of y, because this is total distance squared, and then you divide it by n minus 1, right? Yeah.
What is SS?
SS what?
What is SS? And what do the headers stand for? Like
This
SS?
one?
Yeah.
Sum of squares, and this is mean of square. Okay, and then I don't want to go over too much about the other parts. I think the other parts are pretty straightforward.
Oh, do you like?
Oh, yeah. And then we, I think we have like a little bit of time to cover dummy variables and interaction variables. I think it's really important. So when you run the regression, prestige 10, I female, and then female's coefficient 2.28, right? So how would you explain it? How would you interpret that coefficient? Women, on average, have 2.228 more points of occupational prestige score. It's actually a puzzle for related scholars, actually. Occupational prestige score is high, but gender wage gaps and everything, so it's a puzzle. And then standard error is 0.637. And I wouldn't go over how to calculate this one, but the t statistic is this one, which is okay. Then you would have t distribution. You would draw a t distribution with the degrees of freedom of n minus k, and then find 3.59, and then get the p-value. And p-value turned out to be less than 0.0001. So we reject the null hypothesis at the significance level of 5%. The null hypothesis that beta is 0. Good. Yeah. And interaction terms are also important. Okay. Good. These are the coefficients. Then we can say that you interacted. This means interaction means data, as well as the main terms. It is noted by that the equation that good. Interaction term is basically multiplying these two variables, right? And then include that term in the model. So in this case, what would be the incomes? What would be the incomes effect on occupational prestige score? The answer is it depends on gender, because it can be rewritten as that is the slope of female variable. Ink variable, sorry. So the income variable slope can be different depending on gender. So for women, income variables are more strongly positively associated with occupational prestige score. For men, it's less associated. Does that make sense? So how would you explain this coefficient? Women. No, so this is the coefficient, the slope coefficient. So this is so women are more likely to 0.134 points more on average when income is 0. Yeah. Right. Because yeah. So, and then how would you interpret this coefficient? So it should be the slope of income variable, but only when female variable is 0. So that means that for males, the association between income variable and for males unit increase in income is associated with 0.117 increase in occupational prestige score. That's what it's talking about. Good. And this one should be interpreted as women are, so women are, women's effect of income on prestige score is 0.065 higher than that of males. The effect is changing, not predicted values per se. Does that make sense? They should be interpreted in the sense of the effect changes, not predicted values changes. And the last issue I'll cover is right after you run the right after you're running a regression, and then you would, if you type this command, then it'll give you this matrix, etc., etc. This is variance of beta 0, and then this is covariance of beta 0, beta 1, etc., etc. This is the sampling distributions variance, right? And then this is the joint sampling distributions covariance, which we did not cover in social statistics 1. So you can just think that this is the number you can use for problem sets. Okay. That's all you have to remember. But when you're asked to calculate the significance of effect of female when on our Inc is 100. That's, yeah. When you are asked to female is basically, in that case, income and this one, right? In our regression model just now, just before, right? Now, you are asked to test the significance of the effect of female when on our Inc is 100. So when income level is 100, you are asked to, as if women are more likely to have higher occupational prestige score compared to men. That is what it's asking. Good. So now it's 100. It's fixed as at 100. So the key test statistic is now beta hat and beta hat and the income level and variance then square root. Okay. So if you plug in the numbers, then was 0.134 plus 0.065 multiplied by 100. And according to the beta coefficients covariance matrix table, that was okay. Which looks a little bit weird. Change it. Good. And then you can plug in the numbers. Variance of, this is square root first. Sorry. No. Variance of beta of the female variable is 0.77. And then the covariance of this beta coefficient and this beta coefficient is negative 0.1, right? And then you have income factor right here, which is 100. So you have to multiply 100. And then the variance of the 100, I forgot to add sorry. Which is 0.003. 0.003. 0.0003. If you calculate that, you would have the t statistic right here. And then the t statistic would have the degrees of freedom of n minus k. And based off of that, you can calculate the p-value. Okay. Good. Okay. Oh, thanks. Thank you. Okay.